Hello everyone, in this video I am going to talk about linear transformation and their geometrical interpretation, a fundamental concept in linear algebra that help us to understand how matrices actually change space. Linear transformation and their geometric interpretation lie at very heart of linear algebra, and understanding them deeply changes the way one sees mathematics altogether. While linear algebra is often introduced through matrices, vector, and symbolic calculation, its real significance is not found in memorizing formula but in understanding how space itself behaves under transformation. Linear algebra provides a framework for describing movement chains and structure in precise and logical way. And linear transformation are the tool that make this framework meaningful. They allow us to describe how objects move, how shapes change, and how entire coordinate systems are reshaped without losing their fundamental structure. When we speak about linear transformation, we are not talking about ordinary functions that take number as input and give number as output. Instead, we are talking about functions that take vector as an input and produce vector as output. These transformations do not act an individual point in isolation. They act on the entire space simultaneously. This is what makes them powerful and predictable. A linear transformation applies the same rule to every vector in this space, ensuring that the relationship between vectors are preserved even as the space itself. To truly understand linear transformation, it is essential to begin with vector. A vector is an object that possesses both magnitude and direction is usually written as a order pair such as 2, 3. This representation tells us that starting from the origin to the vector moves 2 units in the horizontal direction and 3 units in the vertical direction. Geometrically, this is visualized as an arrow pointing from the origin to a point in the plane. The length of this arrow represents magnitude while its orientation represents direction. This geometric interpretation is critical because it allows us to see vectors not as abstract symbols but as concrete objects that can move, rotate, stretch, or shrink. Vectors are deeply connected to real life. In physics, quantities such as velocity, acceleration, and force are vectors because they involve both size and direction. And in navigation, displacement from one location to another is represented using vector. In computer graphics, every position, movement, and orientation of an object on the screen is encoded using vector. Because vector describes so many real phenomena, understanding how they transform is essential for understanding how systems behave. Vector exists within a coordinate space in two dimensions. This space is defined by x-axis and y-axis, which intersect at a point known as the origin. Every point in the plane corresponds to a unique vector that starts at the origin and the end at that point. When we draw shapes such as triangle, rectangle, or circle on a graph, we actually drawing set of vectors which position relative to one another define that shape. The coordinate grid itself is not just a background, it's a structured framework that gives us many meaning to position and movement. A linear transformation is function that maps vector from one space to another while preserving the essential structure of that original space. Preserving structure means that a straight line remains straight after transformation. Parallel lines remain parallel and evenly spaced points remain evenly spaced. One of the defining of characteristics of a linear transformation is that the original always remains fixed. This property ensures that the transformation reshapes space around the origin rather than shifting it. Linear transformation do not bend. A useful way to imagine a linear transformation is to think of a transparent rubber street with a grid drawn on it. This grid represents that coordinate system When a linear transformation is applied, the robots it may be straight, strong, rotate, flipped, or slanted, but it's never bent or torn. This grid changes shape, but its structure remains intact. This analogy helps explain why linear transformation preserve a straight line and parallelism while still allowing space to change dramatically. Every linear transformation can be represented mathematically by a matrix. Although matrices are often viewed as an array of numbers, their true meaning lies in their geometric effect. A matrices act like a machine that receives space. When a matrix multiplies a vector, it applies a transformation to that vector. The most important geometric insight is that matrix is completely determined by a law. It transforms that basic unit vector that defines the coordinate axis. Once we know where this unit vector go, we know how every other vector in the space will behave. One of the most fundamental geometric effects of linear transformation is stretching. Stretching occurs when a vector moves further away from the origin, causing object to increase in size. During stretching, the direction of each vector remains unchanged, but its length increases by a consistent factor. When the stretching is uniform in all directions, shape grows proportionally and a square become a larger square, a circle become a larger circle. Angle remain unchanged and the overall structure of the shape is preserved. This type of stretching is commonly experienced when zooming in a digital image or a map where everything appears larger but retain its original form. Stretching does not always have to be uniform. In many cases, spaces may stretch more in direction than another. When this happens, shapes become distorted. A square may turn into a rectangle and a circle may become an ellipse. Despite this distortion, the transformation is still linear because straight line remain straight and parallel line remain parallel. Non-uniform stretching appear in many real-world contexts, such as resizing image where width and height are scaled differently or modeling physical material that stretch more along one direction under stress. Closely related to stretching is shrinking, which can be thought of as its opposite. Shrinking occurs when vectors move toward the origin, causing object to decrease in size. During shrinking, the direction of each vector remains unchanged, but its length decreases proportionally. When shrinking is uniform, shapes reduce in size while preserving their proportion. This is similar to zooming out on digital map where sighting roads and landmark appear smaller but maintain their relative position. Shrinking is widely used in image compression, resolution reduction, and data normalization, where values are scaled down to manageable range without altering their relationships. Stretching and shrinking together are often referred to as scaling transformation. Scaling changes the size of object without altering their fundamental structure. Because scaling preserves proportions, it is one of the most intuitive and widely used linear transformation. Another important type of linear transformation is rotation. Rotation changes the orientation of object without changing their size or shape. When a vector is rotated, its direction changes but its length remains the same. Distance between points remain unchanged, as do angle between vector. Because of this, rotation is known as rigid transformation. A rotated square is still a square and rotated triangle is triangle. Only the orientation changes. Rotation is essential in many real-world applications. In computer graphics and video games, rotation is used to turn character, camera, and object smoothly. In robotics, rotation describes how joints move and how robotic arms change orientation. In physics, rotation is used to model spinning objects and circular motion. Even in everyday life, The rotation is easy to observe when turning a book on a table. The book remains the same size and shape. The book remains the same shape and size, but it faces a different direction. Reflection is another important linear transformation that produces a mirror image of objects. When space is reflected across a line such as the x-axis or y-axis, vectors on one side of the line are flipped to other side. Reflection preserves size and object but reverse orientation. This means that it becomes right or up becomes down. Depending on the axis of reflection, reflection is easy to understand through the example of looking into a mirror. Your reflection has the same size and shape as you, but the movement appears reversed. Reflection is widely used in image processing, symmetry analysis, and computer vision. In architecture and art, reflection helps to create balanced and symmetrical design. In physics, reflection play an important role in the study of waves and optics. Shearing is perhaps the most visually striking linear transformation. Shearing slants space in one direction while keeping another direction fixed. As a result, angle changes, but parallel line remains parallel. Rectangle often become parallelogram and square becomes slanted shape. Even though shapes may look heavily distorted, shearing is a still linear transformation because it preserves the fundamental structure of a space. A common everyday example of shearing is italic text. When text appears slanted to the right or shear transformation has applied. Another intuitive example is pushing the top of a stack of cards sideways while keeping the bottom fixed. The stack becomes slanted but the card remains parallel. In engineering, shearing is used to model forces that cause layers of material to slide past one another, such as during earthquake or mechanical stress. By understanding stretching, shrinking, rotation, reflection, and shearing, we gain insight into how linear transformations shape space in predictable way. These transformations do not tear or bend space. Instead, they preserve its underlying structure. This is why linear transformations are so effective in modeling real-world systems. Linear transformation appear in countless an object that has both magnitude and direction. In two-dimensional space, a vector can be represented as an arrow starting from the origin and pointing to the specific point. For example, the vector 2, 3 start at the origin and move 2 unit in x direction and 3 unit in the y direction. Every point in the plane can be thought of as a vector, which make vector the basic building block of linear algebra. Vector exists in a coordinate space. In two-dimensional space, the coordinate system is defined by x-axis and the y-axis. The origin is the point where the both axes meet. Using this system, we can describe the position of any vector or shape. Linear transformation operate within this coordinate space and describe how vector move from one position to another. A linear transformation is function that take vector as an input and produce vector as an output while preserving the structure of space. This means it does not bend or curve object. A straight line remain straight, parallel line remain parallel, and the origin always stay fixed. Linear transformation only stretch, shrink, rotate, reflect, or shear space. For a transformation to be linear, it must satisfy two important properties. The first property is additivity. That means that transformation This means that transforming the sum of two vectors gives the same result as transforming each vector separately and then adding the result. The second property is scalar multiplication. This means that scaling a vector before applying the transformation gives the same result as applying the transformation first and then scaling the result. This property ensures that the transformation behave in predictable and structured way. Every linear transformation can be represented using a matrix. When a matrix multiplies a vector, it applies a transformation to that vector. The most important geometric idea here is that a matrix tells us where the basic unit vector go. In two-dimensional space, the unit vector are 1, 0 and 0, 1. Once we know how these two vectors are transformed, we automatically know how every other vector in this space will be transformed. To understand this better, imagine transforming a square drawn on a graph paper. When a matrix is applied, the grid itself changes. The square may become larger, smaller, tilted or rotated, but it transform follow the same rule applied to the basis vector. This is why understanding transformation geometrically is so powerful. Let us now look at some common type of linear transformation and understand their geometrical effect using examples. The first type of transformation is scaling. Scaling changes the size of object. For example, if we scale all vector by factor of 2, a vector like 1, 1 becomes 2, 2. Geometrically, this means the entire space is stretched away from the origin. Shape become larger but their angle remain the same. If we scale by factor less than 1, such as 1 half, object shrink toward the origin. If scaling is different along the x and y direction, shape stretch unevenly, turning a square into rectangle. The second type transformation is rotation. Rotation turns vector around the origin by a fixed angle. For example, rotating a vector by 90-degree counterclockwise moves it to a new position while keeping its length unchanged. If we rotate a square, the square remains a square but its orientation changes. Distance and angle are preserved during rotation. This type of transformation is commonly used in computer graphics, robotics, and physics simulation. Another important transformation is reflection. Reflection flips object across a line such as x-axis and y-axis. For example, reflecting the vector 3, 2 across the x-axis produces the vector 3, minus 2. Geometrically, this creates mirror image of the original object. The size and the shape remain the same but the orientation change. Reflection keep भइरहेछ The size and the shape remain the same but the orientation change. Reflection is useful in studying symmetry and in image processing. The next transformation is shearing. Shearing slants object in one direction while keeping one axis fixed. For example, a rectangle may turn into parallelogram under a shear transformation. Unlike scaling or rotation, shearing changes angle but keep parallel lines parallel. Shearing is commonly used in animation, typography, and graphical effect. By examining these transformations visually, we can see how matrices affect not just individual vector but the entire coordination space. The grid itself may stretch, rotate, or tilt, but its structure remains consistent with the rules of linear transformation. Linear transformations are not just theoretical concepts, they play an important role in economics and data science. They allow complex systems to be described using simple mathematical rules. Understanding these transformations geometrically enable us to predict outcomes, design better systems, and develop deeper institutions. In conclusion, linear transformation provide a power way to understand how space changes under matrix operation. By focusing on geometric interpretation rather than memorization, linear algebra become intuitive and meaningful. Matrices are not just collection of numbers, they are instruction of reshaping space. Understanding linear transformation allows us to see mathematics not as abstract symbol but as precise language for describing the world around us. Thank you for your attention.